Okay, let us now start the exercises. The first one is quite easy, and in fact it comes with a minus sign also as superfix to indicate this easiness. We have to find the number of edges in the complete graph Kn here. Now because we are to treat the empty graph with disregard, this has already been decided in the text. So we start our n value with n equal to 1. So K1 is of course just one vertex and no edge. So K1 has no edge. The number of edges in K1 is 0. And when n is greater than or equal to 2, then the complete graph Kn has all the possible edges. Now, since each edge corresponds to two distinct vertices, so naturally there will be this many edges, which is equal to this binomial coefficient n choose 2, that denotes the number of ways of choosing two objects from a list of n distinct objects. So that many edges will be there in Kn, and that's just it. And let's now see the second one. The second one is not that easy, it's normal. So here first of all a natural number d is given, and then we are considering the set V, which is this Cartesian, you can treat it as the Cartesian product of d copies of this set. But instead of considering ordered d tuples, we are just correspondingly going to consider a number, a string of zeros and ones, which we are calling sequences. They are the elements in V. So that means V is the set of all 0, 1 sequences of length d. Okay. Now we are next going to consider a graph on V, that is a graph with V as its vertex set, in which two such sequences will be adjacent, that is they will form an edge if and only if they differ in exactly one position. Right? For example, you have two such sequences. Let me give you one example. Say D is 3. And you look at these two sequences 0, 0, 1 and 0, 0, 0. Because these two sequences differ only in the third position, so according to this rule, these two vertices will be adjacent in this graph. Whereas if you look at this vertex and this vertex, for example, where the sequence terms are all 1, then these two will not be adjacent, because these two differ in not one position but two positions. In the first position also the digits are different, in the second position also they are different. So like that we can get a graph, and this graph has a name. It's called the d-dimensional cube. Now for this graph we have to determine the average degree, number of edges, diameter, girth and circumference. So let's see how that can be done. Solution. Now before we start the solution, it will be nice if we give some notation to this graph. Let's call it QD. Okay, let QD denote the d-dimensional cube. Let QD denote the d-dimensional cube. So the very first thing we are going to note is the number of vertices in QD, that is its order. Note that the order of QD is equal to the number of vertices, which is just simply the cardinality of the set V, that is equal to 2 to the power d. And why are there 2 to the power d number of such sequences? That's because if you look at such a sequence of length d, it will look like this now, a d, where each ai is either 0 or 1. Now since each such ai can either be 0 or 1, that means each one of them has two choices and the ais are all independent of one another. So in total there will be 2 to the power d such strings, such sequences that can be chosen, in which you can change the zeros and ones in many different ways. So that's why that many strings or that many sequences will be there in the set V, which is the vertex set of our graph. So the order of the graph is 2 to the power d. We have not been asked to find the order, but it will help us. Okay, now we want to calculate the average decreases. For that, let's see what the degree of a single vertex is. For any vertex x equal to a1, a2, ad in QD, not writing explicitly in V of QD, because this kind of abuse of notation we are allowed to do. Okay, it just simply means that X is a vertex in the graph QD. So for any such vertex, there exists exactly d vertices in QD, each of which differs from X in exactly one position. The question is how? In exactly one position. That's because you see, you can imagine a vertex that differs from X in exactly the first position, in which these second digit, third, if we call these things digits, okay, the second digit, third digit, and so on, the dth digit are all the same, are all just this. But the first digit is the other number. If a1 is 0, then in that vertex, the first digit is 1. And if a1 is 1, then that digit is 0. So there is one vertex corresponding to the first place where it differs from X. Similarly, you can find other d minus 1 such vertices which differ from X in the second position, third position, and so on in the dth position. And that's just it. So there will be precisely d vertices in QD that differ from X in exactly one position. And that just means what? That means that these are precisely the vertices that are going to be adjacent to X in our hypercube graph, I mean d-dimensional cube. This graph is also sometimes called hypercube graph. Hence, so we can just simply write because of this, the degree of x is equal to d. But x is just any one vertex, any vertex in QD, right? So that means all the vertices in QD must have degree exactly d, which means that QD is a d-regular graph. Let's mention that this is a d-regular graph. So yeah, now it's easy to find the average degree. The average degree of QD now will be just this 1 over the number of vertices times the sum of the degrees. So how many vertices are there? 2 to the power d. And because each vertex has degree d, so the numerator is just 2 to the power d times d. So that gives us this. So that means QD has average degree equal to d. Okay. Next, so that is just average degree. Next, what else we have to find? Number of edges. Now before we go for that, let us just note that the smallest possible value of d is 0, because in this text 0 is a natural number and d is a natural number. So let's handle that case separately because it's just one case. Note that since, okay, by the way, what will it be actually? What is Q0? In fact, what is this? Because we are not treating this as a Cartesian product, although it is, but treating the elements in it as strings of digits, strings of zeros and ones. This denotes the set of all such sequences or strings of zero length, and there is one such string which is the empty string, if you denote it like that. If you treat this set V as a Cartesian product, then also there is precisely one element in this, the zero tuple of zeros and ones. Actually in that tuple there won't be anything, but still it exists, and in that case the cardinality of this is 1. So that means in Q0 there is precisely just one vertex and nothing else, which means that it is just K1. Okay. Now since Q0 is just K1, so we can write down the quantities for K1. The size of the edge set, that is the number of edges, is 0. Then we have diameter. Diameter is also 0 because the only vertex is that vertex, the empty string, and its distance from itself is 0, and that is the largest distance possible in the graph. So that is the diameter. And because there is no cycle, only one single vertex, how can there be a cycle? So the girth by definition is infinity, and again because of the lack of any cycle, the circumference is 0 by definition. So now that we have found all the things for d equal to 0, we can assume that d is at least 1. So we now assume that d is actually, we could have done this before finding the average degree, but anyway, and in fact, if you think of the average degree of q0, q0, what do you get? If you just simply apply the definition of the average degree, then it will be the degree of that single empty string or whatever you want to call it, divided by the number of vertices, which is 1. Now that single vertex has degree is 0, so it is 0. So that means the general formula that we have found for the average degree agrees with this case, so there is no problem. Okay, so now we want to find the number of edges in the general QD where d is at least 1. We have, now if you just simply think of it directly, it seems like it's really confusing. How can you follow the rule that tells us which vertices are going to be adjacent? From that, how can we figure out how many edges are there? But you need not go in that direction. You note that you can apply this trick. The number of edges in QD is equal to the number of vertices in QD, of course, times that average degree, that other average degree, which we denote by epsilon, because epsilon is the number of edges divided by the number of vertices. Unlike this one, which is the ordinary average degree, there is that other average degree which denotes the number of edges divided by the number of vertices. It measures the average number of edges per vertex. And we also know the relationship between epsilon and d, which is just this. The epsilon value is half of the d value. And now since we already know this, so immediately we have our answer. This is 2 to the power d times 1 over 2 times d. So this is just this. Okay, without going through the hassle of figuring out how many edges are there, this way we can quickly find out. So that is with average degree and number of edges. Now we want to find the diameter. Okay, but before finding the diameter, we have to figure out how to calculate the distance between two vertices in a d-dimensional cube. Let us now draw a figure. Let's see how the graphs actually look. Because our d now starts from 1, so we are going to accordingly start. If you are thinking of strings of length 1, then you just have two such strings, 0 and 1, and they give us two vertices. And because these two strings differ in their only position, that is the first and only position, so according to the rule they should be adjacent. So this is our Q1. In Q2 we will have strings of length 2. So there will be 4 vertices corresponding to these strings. Zero, 0, 1, 0, 1, 1 and 0, 1. This is not 10 and this is not 11, that of course you understand. Because here only the first positions differ, so these two will be adjacent. Similarly, here also only the first two positions differ, so these two will be adjacent. Just like that, here between this and this only the second positions differ, so these will be adjacent, and similarly the other two will be adjacent. And you can see that between this one and this one both the positions differ, so they will not be adjacent, and similarly this and this will not be adjacent. So this is our Q2. So Q1 is just the path P1 of length 1, Q2 is just the cycle C4. Now how would Q3 look? In Q3, I think it will be better if I draw it somewhat in a more, let us draw a larger diagram so that you can see why we call it a d-dimensional cube. Now here let's now name the vertices. Say this is 0, 0, 0, okay, 1, 0, 0, 0, 1, 0. This one, let's name this one 0, 0, 1. Then 1, 1, 0. I have to name them actually carefully, because otherwise I won't be able to show why it's a cube, why it looks like a cube. And one more, right? So this will be 0, 1, 1. Okay, now we are going to apply that rule for adjacency and draw the edges. We are to draw only edges between those vertices where the strings differ in only one position. Because these are graphs, you can draw them in any way you want, maintaining adjacency, but it looks good this way and it shows where this idea is coming from. So you can see that this is a 2D representation of a cube, something that we often draw while we have to draw a cube, although it doesn't look like a perfect cube, but you get the idea. So you can see that we have only drawn edges between strings that are that differ in only one position. For example, here between 0, 1, 0 and 1, 1, 0, only the first positions are different. The second position is 1 in both of them and the third position is 0 in both of them. That is the case with the other things. Okay. So this is a one-dimensional cube which does not look like a cube at all. It's a two-dimensional cube which looks like it's supposed to look like a square if drawn properly. And this is a 3D cube. Now you can imagine a 4D cube also. I mean, at least in this setup. Now, do you see one thing? That the 4D cube actually will just simply look like this. I am using ruler because otherwise it will get too messy and you won't get the idea. Okay, now it's not just simply these two copies of Q3, but other edges are also there. Now let's notice one pattern, and the pattern is just this. Do you see that there are two copies of Q1 in Q2? For example, this one and this one. And they have been joined by two other edges. Now, how does one create this Q2 from two copies of Q1? You can imagine the thing like this, that this is one copy of Q1, this is another copy of Q1. And as usual, we have 0, 1 and also 0, 1. Now, what we can do to distinguish these two things is that we can add extra digits to these strings of length 1. For example, in this copy you can consistently add 0. In this copy you can consistently add 1 at the end, right? And then you join the corresponding vertices in the two copies. So you join this one and this one and this one and this one. Why are this and this corresponding to each other? That's because originally both of them were 0. These two corresponds because originally both of them were 1. Is the same thing happening while we have Q3? I mean, can we similarly construct Q3 from two copies of Q2? Yes, we can. So one copy of Q2 you see here, the other copy of Q2 lies here. Now, if for a moment you forget about these last digit zeros, and in fact, in the upper plane, if I call that, the last digit is 1. Do you not see two copies of Q2? 0 1 1 1 1 0 0 0, 0 1 1 1 1 0 0 0, 0 1 1 1 1 0 0 0. You see exactly the same thing, just like these two. And then what you do, whatever we did here, 0 0 0 0. We augment all the strings in one copy with 0 at the end, and in the other copy we write 1 at the end. That creates Q3 from two copies of Q2. Similarly, if one goes, then one would also end up creating Q4 from two copies of Q3. Just simply this. I mean, you just simply you can of course name the vertices similarly, and after doing that, what else you do? You write an extra one at the end of all the strings that you see here in the upper copy, and you write an extra 0 at the ends of the strings, all the strings that you see in the lower copy, and then you make corresponding vertices adjacent. Okay, all of them. If you do this process and complete it, then the resulting graph will be Q4. And keep in mind one more thing, are we really justified in doing this? And what we end up having, is that really Q3? Let's see. In the original two copies of Q2, for example, say in this upper copy, now that we have augmented the strings with an extra 1, has that affected adjacency in any way? No. Why? Because originally between 0 1 and 1 1 there was an edge in Q2. That's because these two strings differed in only one place. By adding an extra same thing, that doesn't change. Okay, so in the larger graph also they continue to be adjacent. The same is the case with the lower copy. And when we are looking between copies to add these extra edges, then the only place where we see a difference in these strings is the last place, because in this plane we consistently have only ones, in this plane we consistently have only zeros. So naturally the corresponding vertices will now be adjacent. And you also end up having the number of vertices required in this higher Q3 when you are coming from Q2. Why? Because in Q2 you have 4 vertices. In Q3 you should have 4 means 2 square. In Q3 you should have 2 cube vertices. That we are getting because we are doubling the number of vertices by taking 2 copies, right? So that's why this is in fact Q3, and from Q3 you will get Q4. In this way you can get higher and higher dimensional cube graphs. So based on this idea, if one thinks a little bit more, one can figure out how to calculate distance between 2 vertices in a d-dimensional cube. But how? It may not be immediately obvious how, but if you just look at Q2, the distance between 0 0 and 0 1 is 1, because these two differ in only one place. These two differ in 2 places. The distance is 2. Let's see one more. The distance between 0 0 0 and 1 1 1 is 3, because you can find a shortest path like this, and this. or this, and there are many such paths, but they all have length 3. There is no shorter path. 3 is the minimum length path. That's because they differ in 3 places. Whereas if you see the distance between 0, 0, 0 and 0, 1, 1, then that distance is 2, or this way 2, because they differ only in 2 places. So this gives us an idea of how to find the distance between 2 vertices in general QT, and that is our next claim. Okay. Next, before we get rid of these things, you note one more thing. Because of the way we have recognized that the higher QDs can be constructed from the lower QD minus 1, 2 copies, one more thing that you should note here is that because adjacency is not affected, so the copies of Q, for example, the 2 copies of Q2 in Q3 that you find, they are induced subgraphs. If you collect only these 4 vertices in the lower level, if I call that, okay, just for the sake of understanding, and see what subgraph these 4 vertices are inducing, then that will be Q2 itself. So in the larger graph, you do not get any new edges in any one copy of your lower dimensional cube. New edges, of course, you are getting, but between copies, not within a copy. So this is an induced subgraph, that is also an induced subgraph. Here also, if you look at the subgraph induced by this vertex and this vertex, that is just one copy of Q, and the same is the case here also. And if you go one step back, you are looking at 2 copies of Q0, single vertex. Okay. Next, for x equal to A1, A2, AD, and y equal to B1, B2, BD in QD, we claim that the distance between them in the graph QD, of course, is this sum AI minus BI as I varies from 1 to D. That's because this keeps track of how many places there are in which the 2 strings are differing. If they are not differing, then that contribution will not be counted because it becomes 0. Otherwise, it becomes 1. So, for example, these 2 strings differ in 3 places. So, if you calculate this for these 2 strings, then you are going to get 3. Now we are going to prove this. And in proving this, we of course are going to apply induction on D, and in doing so, in carrying out the induction step, this fact that QD can be used to create QD plus 1 will be used. The claim is clearly true for D equal to 1. But why? How is it clearly true? You just see it like this without writing anything. This is our Q1, right? So we can have three choices for x and y. One of them is x and y are both 0. Then in this sum, for this case, there is just one term, which is this. So that is 0. And in fact, the distance of 0 from 0 is actually 0. So that matches with this formula. And if both of them are 1, then also the distance is 0. It should be 0 by definition of distance. Okay, but by this formula, also it is 0. Whereas the other possible choice is that one of them is 0 and the other is 1. Order, of course, does not matter. You write 1 here and 0 there, that does not matter. Here the distance should be 1, that we can directly see from the graph, but also by the formula it is 1. So that means this in fact is true when d is equal to 1. That's what we have written. It's clearly true for d equal to 1. Let it be true for some positive integer d. Okay, let the formula be true. So this is our induction hypothesis. Now let what are we going to, let's call them a and b. A equal to u1 u2 ud plus 1 and b equal to v1 v2 vd plus 1 belong to qd plus 1. Now we have to verify that the same is true for the distance between a and b in qd plus 1. And now two cases arise. If it may happen that the last two digits are the same, if ud plus 1 and vd plus 1, well, okay. Actually, I got carried away in explaining that construction, but I should have written about that here, no? Let me do that now. For that fact must be mentioned, otherwise how can I use it? For any x1, x2, xd in qd, we associate two sequences. That is, two sequences means one which has an extra 0 at the end and the other which has an extra 1 at the end. In qd plus 1. So the vertex set of qd plus 1 can be partitioned into two sets of equal size, equal cardinality. Two sets means two subsets of equal cardinality such that the subgraphs they induce in QD plus 1 are both isomorphic to QT. Because of this association, for example, Q3 can be, its vertex set can be partitioned into those 4 vertices and below those 4 vertices, so that the subgraphs that these two subsets induce, both of them are isomorphic to Q2. And QD plus 1 can be recovered from these two copies of QD by adding these edges. Edges means the edge between this one and this one. How do I write that? I have to just simply use the notation. If I just simply write this followed by these things, then it will be very confusing. Or, okay, I can use parentheses, right? Just to enclose one vertex, whatever we have in one vertex, just to enclose them, I can use this. So this is one vertex followed by the other vertex. So this is one edge. So that means by adding these edges between those copies, we can recover QD plus 1 from those two copies of QD. Okay, now we have concretely written how to get QD plus 1 from QD. Now we can carry out our induction step. So induction hypothesis we already have. Let the claim be true for some D. Now let A equal to U1, U2, UD plus 1 and B equal to V1, V2, PD plus 1 B in QD plus 1. Now case 1. If UD plus 1 is equal to VD plus 1, then what? Then from that construction we know that both A and B either belong to the lower level, that means in one copy of QD, or in the upper level, that is in another copy of QD. Then both A and B are in any one of the two copies of QD in QD plus 1. Now finally, since QD is an induced subgraph of QD plus 1, so okay, let me write and then you will realize what I am trying to say. Since QD is an induced subgraph of QD plus 1, we have this fact. So mentioning this fact that QD is induced in QD plus 1 allows us to use the fact that the distances have not changed when we are treating QD as a single graph in its own right and as a subgraph of QD plus 1. The distances between vertices, they do not change. So what we are trying to now say is this: the distance between A and B in QD plus 1 is equal to the distance between their corresponding vertices in QD, in the copy of QD, where these two are lying in QD. That is, these are UD and VD. I mean, the way we are naming things in the lower dimensional QD copy, you will of course have strings of length D, so the last digits are to be neglected. Okay, so this is the thing. But now you can use your induction hypothesis, and the induction hypothesis says that this is equal to summation Ui minus Vi, where I varies from 1 to t. But now see how nicely all the things fall in place. Besides this one, you can also write another term, which is this. That's because it is 0, they are equal, and that allows us to write the sum as this sum. So that means our formula has been verified for D plus 1 in this case. Now we have to consider the other case. The other case, of course, is just this. If UD plus 1 is distinct from VD plus 1, then A and B lie in different copies of QD in QD plus 1. Maybe one of them is lying in the upper level, upper copy, and the other one is lying in the lower copy. I need some ink. Just give me a moment. Now what do we do? Now think of that little diagram again. You have another box here. Say your A is one of the vertices in the upper box, say this vertex, and B is say any other vertex in the lower box. So A lies in one copy and B lies in the other copy. So how does a shortest path between A and B look? There will be many such paths, but among them there will be particularly one path which will go like this. What you can do is that in order to find a shortest path and hence to minimize its length, instead of unnecessarily roaming around in this copy from A, because you have to get to B as quickly as possible. So from A itself you make a jump which is there, and that is the jump from A to its corresponding vertex in the lower copy, and then you roam here in order to reach B as quickly as possible. So that is why a shortest path between A and B is the not vertex but edge, is the edge, or you can do one more thing also. You can because I have written things in that manner, you can think of reaching A from B also. That way also you can imagine. So what you do, you make the jump from B to the corresponding vertex in the upper copy, and then here you find the shortest path between this vertex and A. So that means a shortest path between A and B will be a shortest path between A and this vertex followed by this edge. Let's write that. So a shortest path between A and B is, now the edge will come afterwards, is a shortest path between, let's write the vertex corresponding to A in this copy, in the copy where A is lying, by neglecting the last digit from our string, between U1, U2 up to UD. And now what is this vertex? That would correspond to B, but it lies in the other copy. It would look like this. V1, V2, VD, and then, well, if you have VD plus 1 after this, then you are just writing B, but it's not that. So UD plus 1. Oh, in that sense, I have to write D plus 1. I mean, I cannot neglect this thing, the last digit. Okay. So that is just simply A. Between the shortest path between this and this in QD, that means in one copy. So this is one QD, this is another QD, followed by the H. VD UD plus 1, and you understand that I have to write these two things together. but because of lack of space I am writing like this, and v1 v2 up to vd plus 1, or because that is just simply b here, I can write b here. Okay, so that is the shortest path. So in this case, okay, now I can just simply modify this calculation itself. So in this case, this distance is equal to, but I need more space, is the distance between this will look a little strange and not rigorous, but you will understand what I am writing. So A is just that, u1, u2, ud plus 1, and this vertex v1, v2, vd, ud plus 1. Actually these are two elements in qd plus 1. So using qd here is wrong, but by writing qd here I just simply mean that the distance is going to be calculated in one copy of qd. Okay, so the notation is a little wrong, but to make sense of all the things I have just written like this, plus the distance between this and b, which is 1. Why is it 1? That's because it is just a single edge. Let us now see what is coming out of this. Okay. Now in calculating this distance, we can use again that fact that qd is an induced subgraph in qd plus 1. So that's why this distance is just the distance between this and vd. Note one thing carefully, that we are not using the formula here. In writing this in place of this, we are using the fact that qd is an induced subgraph in qd plus 1, and that's why the distance between two vertices when treated as two vertices in qd plus 1 but belonging to the same copy of qd is equal to the distance between them when treated as vertices in qd, in that copy of qd. That's why we are able to write this. Okay, so now in place of 1, note carefully that we can write ud plus 1 minus vd plus 1. Why? That's because these two are different digits. Since each one of them is either 0 or 1, so this difference, regardless of what they are, will always be 1. And it is here that now we are able to apply the induction hypothesis and write this distance as this term. And hence finally we have what we wanted to show. Okay, so that completes the induction and proves our claim. Thus, the claim follows by induction. Okay, that's arguably somewhat we have worked hard. But what is the payoff? Now, what is the advantage of having this fact? From this, claim, we can see that if A and B are two vertices in QD such that they differ, because their strings differ in all the places, all the D places, all the D positions, and such pairs clearly can be found. In fact, you can take these two vertices. A is that string where all the digits are 0, and B is that string where all the digits are 1. That's it. Then the distance between A and B in QD is going to be, so in our sum of D terms, all the terms are going to be 1. So this is equal to D. And that is the largest distance possible due to the nature of this formula. There are no cancellation or anything. Any such term contributes either 0 or 1. So the maximum contribution that you can have is D number of ones. So D. Hence, the diameter of QD is D. Okay, so we have found the diameter. Next comes, after diameter we have girth and circumference. Should I do it in this video, or let's stop here itself, and because it will take some more time. Okay, although maybe not this much time, but significantly longer. I mean, I'm not able to just write 2 and 3 more lines and then complete the solution. So let's just keep it in this incomplete state here itself, and with girth and diameter we are going, with girth and circumference we are going to come back in the next graph theory video, whenever that comes. And we of course are going to see other exercise solutions also that come after this. So that's just it in this video for tonight. And tomorrow we have our usual algebra exercises. So tomorrow we are going to solve ring exercises from Gallian. So see you tomorrow with that. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.